Hello everyone, I'm Yao Chen. My presentation is about the numerical study of the flame propagation in high-speed non-uniform flow field. This is the background of my work. In a variable cycle engine, the inflow is divided into many ducts and finally merged into together before the afterburner. So the inlet of the afterburner would have a very high velocity and temperature non-uniform. My work is aimed to investigate the impact of the non-uniform and find out the way to control and use it. My presentation will be made in 6 parts. Firstly is the model I used in this study. It's a square burner with a cavity strut stabilizer. The nozzle is set on the side of the strut and the backstep of the cavity. And the flow field of the fuel is all the same. The mesh is verified to satisfy the Pop's principle, which means there is over 80% of the turbulence energy is solved. The turbulence simulation method is verified with this typical black body combustor. The experiment data, the velocity flow field is being measured with the PIV, and the images are very high quality, so the result is very credible. We've compared the Smagrinsky one equation ID and the Weil models, and found out that the Weil model has the best performance. The spray and combustor model is being verified in our previous work, and the simulation results have a great fit with the experiment data. The combustor model we use is the flameless generated manifold, so-called the FGM. We solve the flamelets in all the scalar dissipation rates. So we have a laminar flameless database. Then we integrate the laminar flame database with our in-house code FM2 Delta. We integrate the mixture fraction with the beta PDF distribution and the progress variable dimension with the direct PDF distribution. And finally, we got a three-dimension turbulent flamelets database. We get a scalar value from the flow field with the transport equations on the left side. And based on these scalar values, we check the timetable we built before to get the combustion message we need. Here is a little problem where we built the laminar flamelets database. Left side is the high temperature condition laminar flamelets, and on the right side is the low temperature laminar flamelets. We can see that the steady flame branch and the unsteady extinction branch is almost the same. There is no big difference. But in the high temperature conditions, the unsteady flame branch has no solution in the low scalar dissipation rates. And because the temperature is too high, so the flame is very easy to be steady. So there is no unsteady flame branch. It may have some influence for the FPV model, since the FPV model needs this branch, but it doesn't have many influence for the FGM model we use. This is the non-uniform velocity inlet distribution we use. We generate this distribution with the Gaussian function. The difference between these three distribution is the position of the peak of the position of the peak. Here's the top peak distribution, the mid peak distribution, and the bottom peak distribution. The different non-uniform inlet can lead to the different non-reacting flow field. We can see the recirculation zone is very different because of the different position of the velocity peak. Besides the fuel and ice mixing is very sensitive to the non-uniform. We can see in the uniform inlet conditions, the fuel is only evaporated around the spray, and since the radial velocity is very low, the mixing is not very good. It's just like a separated rich zone. However, in the non-uniform conditions, the fuel is very mixed, well mixed. Because of the non-uniform inlet can cause the higher radial velocity. The non-uniform velocity inlet can not only cause the non-reacting flow difference, but also have a equivalent ratio influence. Let's take the mid-peak distribution as an example. Most of the air goes is in the mid zone, and there is very little air in the top and bottom. But the fuel is all the same at the radial direction. So here is a very rich zone at the top and the bottom zone, and a very lean mixture in the mid zone. And this non-uniform of the equivalent ratio is very bad for the combustion and the flame propagation. However, though we have this problem, but the non-uniform inlet have a great influence of the fuel air mixing. We could tell from the picture that in the uniform inlet conditions, the fuel does not mix very well. It's just a separated rich zone. But in the non-uniform inlet conditions, the fuel and air is mixed well. It's mixed together, and this is good for the combustion and the flame propagation. So in the next part, we'll see which influence is stronger. Before the result, I'll simply introduce the ignition model we use. We simply set a fully developed flame kernel in the igniter to simply modeling the energy deposition and the kernel development process. The flame front goes like this from the low progress variable to the high progress variable during the flame propagation. And here is the result of the simulation. We could tell that the flame propagation speed is much faster while I ignite in the mid position. We quantify the flame propagation speed with the OH radical of the slice near the bottom wall. As a result, the bottom peak distribution has the fastest flame propagation speed. Firstly, this is because the good mix of air and fuel in the non-uniform conditions. Besides, the velocity is much higher when the non-uniform inlet, especially the bottom peak velocity distribution. The radial velocity is much higher, which is very helpful for the flame propagation. So in conclusion, the non-uniform inlet condition is good for the flame propagation and the fuel and air mixing. In our future work, we want to try different structures and the set of nozzles to get a better performance stabilizer. And for the simulation, we may try the non-adiabatic and unsteady flameless method to better modeling the energy deposition and the kernel development process. Thank you. That's all.